This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Instead of giving a long introduction, can you put the camera on the abstract speaker? Because I'd rather hear him speak. For a number of reasons. Can I have the overhead camera? Lock. Anyway, he has background from the UK and is now local, working on things with LMK and this company. And just give me something to display your abstract. Because most people, let me put it this way. Anybody did not read his the abstract on the website? Oh, cool. Since I'd rather do that while you can read it and we have a speaker. So I'm sorry with that introduction, please.
Thank you, Martin. Okay, well, that's going to serve as the entire introduction, I think. So what I wanted to do today was, rather than present any small, coherent story about a small, easily understood artifact, I thought I would make a survey of various influences that are pertinent on the thinking of myself and my colleagues today as we embark on a rather ambitious project to reinvent the way we interact with computers and program computers. So in the talk and slides today, I will be showing some algorithms, some work going all the way back maybe 50 years ago, which is intended really for your offline contemplation afterwards. I know the slides are available from the EE380 website, so please feel free to download those and criticize me in batch mode afterwards. And I hope this will be motivation for any of you that are practically inclined to go away and experiment with some of the ideas that I'm talking about today, if you have not already done so in the past. And there will be pointers to useful information. And go away and make things to know, not just to have, because when you do something, you don't just understand it, you believe it. And there's a very big difference between understanding and believing. And along the way, I will show some pertinent artifacts from the last 50 years of ancient computing history. So even though this is EE380, if you go away feeling that you've been in Computer Archaeology 101, I will completely understand. So about the group that I belong to, vpri.org is our website. You can find a lot more than I have time to explain on that website. In short, one of our goals for the next 5 years is to build a complete practical personal computer system. Everything from the user interface and the way the users interact with computers, all the way down to the thing that tells the metal how to run everything in 20,000 lines of code. That's a ballpark figure, but it would be nice to get it below 20,000 lines of code. And this is one stepping stone on the way to a reinvention of the way we look at computers, which these days really are just dinosaurs, gigantic things that should be a lot smaller and a lot more beautiful than they actually are. And so I'll talk a little today about the language and system approach to what we're doing. And this can be summed up by saying that the system should be the curriculum. And its emphasis is not so much on functionality, but on the ideas and the ideals of what the system should be, intended to be comprehensive so that anybody with a little background can go away, look at the system, and understand the system simply by inspecting it. And it should be its own model, so that it implements, the model that it implements is also the model of implementation that implements it. So if you like, it's a system to learn about systems or an exploratorium. And if you haven't been to the exploratorium in San Francisco, you really must. It's a fabulous place. So our approach, in contrast with current computing systems, which can be seen as really functional devices that are intended to get a job done, and nobody really cares too much about how beautifully the job gets done, there is a list of adjectives there that I think describe our feeling about current computing systems. And certainly current systems are not good models of what a computing system ought to be, because a model is most useful and most powerful if it can capture the entire phenomena that it is trying to describe, and yet be small enough so that with just a small amount of effort, you don't really need to have a PhD in order to understand the model. So powerful enough to completely describe its domain, yet small enough to be comprehensible to an average person. And the question really that we need to address is, can we even begin to build a system that will support our research towards inventing new ways of interacting with computers? Can we even begin to build the system using the conventional programming languages of today? Now, I know there's a mixed audience here, so I was expecting some electrical engineering people, some computing people, so I thought I'd just put up a slide that describes briefly what a computer programming system should do for you. In green, this may be a little hard to see. On the left, we have the source code, which generates by some convoluted process an application that you run. And most systems are designed so you have the illusion of being able to control what happens here by modifying what you feed into it over here. But the reality is, in most systems, we have these two black boxes that are hermetically sealed. We have a language that describes how what you write over here gives you the illusion of controlling what pops out over there, and then an environment which tells you what you can and cannot do when your illusion of control starts to run over here. And if we look at the language side, we have three things that are important. Syntax, which is the words that you use and the combinations of punctuation symbols, etc., that you use to describe your intent. The semantics, which is what that actually means in terms of a sequence of actions that a machine might perform in response to those sentences that you give it. And then what I could call maybe pragmatics, which is how does that then relate to what's happening in the rest of the world? Because if you have a fabulous application that cannot make the toaster turn on and off, then the application and the toaster are both useless. So pragmatics is how do we interact with some external stuff. And all of these are administered by a friendly program, the compiler, that probably has some runtime assist, which gets linked in or otherwise made available to your program. And then this all sits on top of an operating system, some hardware, and then some libraries that are supplied for your reuse. If you're very lucky, you will have a language such as Smalltalk that gives you some user-defined primitive ability, so that if there is something missing in your runtime, or there is something at the limit missing in the semantics of your language, maybe you can understand enough about the implementation to go away and make it for yourself. But that's not really what I will be talking about today. I'm going to be concentrating today on these three things top left, and what I hope to show is that a very simple model of those three things up top left can take away all of the tyranny that is in red and sealed in those black boxes in this slide. So I'm going to give you, normally I like to make this talk 50% demonstrations, but because of the media involved today, I thought I'd cut it down to just one demonstration. So I hope you can see what's popping up on my terminal here. If not, I should say in the slides that are available online, the last 2 pages in those slides contain a typescript of what I am about to attempt. So what I have is a little language that's parse trees. It may look a bit lispy to some people, but actually it's looking at parse trees that have essentially the semantics of the C programming language. So if I ask for the character that offsets 0 in a string, ABC, I get the ASCII value of A, B, C, etc. And anyone who knows C would expect there to be a 0 at the end. That's all very well, and it's a lispy, a schemy, if you like, type syntax. But I may not be inclined to write char at inside lots of infernal silly parentheses very often. I might want to invent my own little bit of syntax, and in many systems it's very hard to invent your own piece of syntax, and the kind of malleability and flexibility that we are talking about creating at every level within the computing experience, I hope to be able to demonstrate right now. I've loaded some libraries into the system, and one thing these libraries allow me to do is, for example, add some rules to the front end of the system that is interpreting what I type to it. And so what I've done here, the code name for this little Lispy type language is Coke, for reasons that I will not explain because I'm on record. And in brief, what I have done is the following. I said with a certain set of rules for recognizing tokens on the input, characters on the input, breaking the stream of text into individual units that have some semantic meaning, using a certain tokenizer, take an existing rule in my grammar, which is called Coke, and then extend it by saying afterwards I can have either a square bracket enclosing an expression, and I will store that in a variable for later use, or nothing, in which case it's just the original expression that I put in. So hopefully what I've done now is taught my system to recognize that if I put something inside square brackets after an expression, I would like it to pretend that I had typed the following. Okay, so a little bit like a macro system, but I don't have time to prove it today, but it goes much deeper than a traditional macro system. So in theory, I have taught my system now how to understand my square brackets. It's not completely transparent in that I have to, in this version of it, tell it to re-enter the interactive loop, but now I should, if I haven't screwed up, be able to say ABC of 0, and here come my characters. I have taught my system a little bit of new syntax. And just to show you that I'm being honest about this, if I were to type the same thing into the original unloaded system, I would get this bizarre error message, which actually really means you're not allowed to put a square bracket after an expression with a single thing inside it. Okay, so that's one of many examples I would normally give, but unfortunately the media today preclude the rest of the examples. If you follow the abstract, there are some URLs on the Colloquium webpage where you can download this software and play with it for yourself. So, if we want to apply this kind of flexibility at every level inside the computing experience, what kind of ways do we have to think about computing? The traditional ways don't really work, and we have to make we have to have recourse to something a little more foundational, and mathematics as usual wins in this sense. And we can start looking at programming not really in terms of procedural languages, etc., but in terms of algebras of meaning. And so an algebra in mathematics abstracts a certain set of operations on a certain domain, a certain set of types, and with that little language that it constructs can do immensely powerful things. And it's designed to emphasize the similarities in the system that it's describing and to brush away the differences, thereby making it of a much larger scope and much more flexible, and to contract the number of things that we actually have to describe in detail in order to get the range of behavior. Now, if we look at the history of programming languages, do I or don't I? Yes, I do. Anybody in the audience who has not obtained a copy of this book, read it, and really understood it, needs to go away and do so, because this book is the foundation of all serious thinking about the meaning of programs. And it came out, I believe, in 1962, and the first author is John McCarthy, who you may recognize as the inventor of lots of infernal silly parentheses. Now, what's wonderful about this book is that it not only describes a programming system, but it describes, using the programming system, how that programming system works. And at the bottom of page 13, you find this wonderful little program written in the system described that has two functions inside it in particular. It has a function eval that says, given a structure in this system, what does it mean to evaluate that structure? And there are some rules that you can see for evaluating simple literals or conditionals. And then if you have a function, a structure representing a function, there is a helper called apply, which is way up at the top, which describes various structures in the system and what their meaning is when applied as a function to a sequence of arguments. Now this is very powerful because it's a simple model. It has just 5 primitive concepts inside it, yet it manages to be powerful enough to be a completely general environment that reasons about itself. Now, there is some bold in here that maybe you can or cannot see. The primitive, or what McCarthy called the elementary functions, are shown in bold. It's a lot more obvious, I think, in the printed notes. In short, it's cons, car, atom, EQ, CDR, and there's one primitive form, you can't see it in bold right now, but he cheats slightly. In order to evaluate a conditional, he uses a conditional. So for those not familiar with Lisp, everything that I just said is to do with structure, with interrogating, comparing, and constructing forms, data structures that describe the functions, and those functions really are the domain of the system. The data structures are kind of secondary. So we have a system for describing functions that depends upon some structural details. In this case, in the Lisp case, the structural details are largely irrelevant. We have a few simple axioms. As long as we understand the axioms, we can then do very powerful things with the theory of functions. However, maybe there's a jewel to this as well. Maybe we can fill in the missing parts, because the missing parts, they gnaw at me. What does it mean to be a list? What does it mean to be constructed? Cons. What does it mean to be the head of a list, the tail of a list? These are the basic things with which the theory reasons, but which are not described within the theory. So the question really that poses itself to me is, can we make a similar theory of structure? And some structure, of course, needs some implementation, which is going to be provided by function, but can we make a theory of structure in which the functions are almost as irrelevant as the structure is in the Lisp story of how functions work, or at least reduced to their simple essentials as they are with the 5 elementary functions in Lisp? So, being from an object-oriented background, naturally my first inclination is, let's just encapsulate things as objects. Let's just say, okay, we have an object that's representing something. We don't really care about how it represents it. All we know is we can ask it a question. It gives us back an answer. So a minimal object looks like the top of the slide. It's a blob of something we know nothing about, to which we can send a message or ask a question, and it will give us a reply. It might say yes, no, 42. It might say nothing for an hour and then give us back a reply. So no assumptions about the object contents, and we can decouple the implementation of our objects entirely from the representation of those objects, because our interface to those objects is purely by sending messages. We don't know, nor should we care, about the internal representation. It's interesting to note, actually, that you can slice this 2 ways. You can either take an object that you know nothing about, and you can pretend that it has state by invoking functionality as messages, or you can pretend that it has functionality by modeling everything as state. And this is what the self language did. It said that an object is just a bunch of slots. However, some of those slots, when you ask for their value, are evaluated. They are active state. Anyway, we go the first route. It's a little simpler to implement. So we can decouple the implementation from the representation. And if we do that in such a way that an object's behavior, that's the little b in a circle, is somehow slightly distinct from the object itself, we can share the behavior amongst many different objects, or we can replace the behavior for an object transparently to anybody who might be using that object. Now this is a very old idea. Just as Microsoft didn't invent the internet, some microsystems didn't invent object-oriented programming either. And if we go back to 1960, we find a paper by Douglas Ross, who was at MIT, I believe, where he describes a way of organizing data structures such that some elements in those data structures contain jump instructions. And those jump instructions transfer control to different points in the flow graph of the program. And anyone who's done object-oriented programming will immediately recognize this as dynamic dispatch. Now, this is the earliest I know of that this was described in the literature, although if anybody has earlier references, I would love to hear about those. From an object-oriented perspective, objects have nice properties. They can manage complexity. They can hide details of the implementation so that we don't need to worry about them until we're ready to. An object with a question mark inside it can even have non-object contents. We know nothing about the contents. Plus they behave as namespaces, we can avoid pollution, etc., etc. But one of the things I like in particular about objects is that there is a certain duality that starts popping out of them when you think about them enough. If we go back to the Lisp in Lisp definition, there is a notion of applying a function to some arguments in an environment that gives this function some meaning. If you look at an object, the object-oriented way of doing this is saying in some receiver object, invoke this function with these arguments, passing the receiver itself as an implicit argument to the computation. So in the Lisp world, this association list that they have is an environment in which function names are bound to function meanings. In the object world, it's a receiver object that has a method dictionary that's doing exactly the same thing. So on that level, functions and objects really are extremely similar devices. So if we go back to our minimal idea of an object, a blob of something with some behavior, how might we represent this concretely to a computer? Well, the way we choose to do it is to place this big blob of something in memory. We have a reference to it so that we can reason with it, pass it around as a parameter, and then before the body of the object, we have a pointer to some other object which is going to give behavior to our minimal object. And these pointers are often called virtual tables because they are tables of pointers to what are called virtual functions. These functions are virtual in that they may not exist directly for any given object. They are one mechanism of sharing behavior between disjoint but similar types of objects. And so a function may be virtual for a given object in that it's not defined for that object but by something that helps that object by sharing the behavior. Now, our one operation that we're interested in these objects is sending a message to the object. How do we do that? Using our simple model. Given a message sent to some object with some arguments, we're going to go find the virtual table, which is at offset -1. Fortran programmers will love this. Offset -1 in the object, and then we ask it to look up the message. So our virtual table object looks up the message we're trying to send, gives us back a method implementation that looks like a function. If we call that function, it's equivalent to invoking the message, sending the message to the object, which will return us a result. So the question is now, how does this operation, this lookup operation, work in our virtual tables? Well, it's a two-stage process. First, we have to find a meaning in that object for the particular message, and this is called a binding or a dynamic binding operation. And it involves sending the message lookup to our virtual table. If we expand that slightly, we grab the virtual table, which is at offset -1, and then typically what is done in object-oriented systems to speed things up, we make a cache, we memorize the results. So these extra 2 lines are simply saying if we find an answer in the cache, send back the answer we've got, otherwise fill up the cache. 2 more things we can do. We can have special kinds of objects that have, for example, an odd address in memory, are sometimes used not to point to data in memory, but to encode the value directly in the pointer, because on many architectures an odd pointer makes no sense at all. So languages like Smalltalk, or some dialects of Smalltalk at least, will put a 1 in bit 0, the bottom bit of a pointer, and then the rest of that pointer is actually an encoding of the object, the value of the integer itself. We can do the same with nil if we choose to do so. But what we have, in order to bind an object to a message, eventually, is the send of a message lookup to the virtual table, where lookup in a virtual table is itself defined in terms of bind. So what we have now is a mutual recursion happening. To send the lookup message to a virtual table to find a method to run, we invoke bind, and then bind itself, in order to work, has to be able to send lookup to the virtual table inside the thing we're trying to look up in. So there's this circularity going on, but it is not really any more violent than the circularity that is going on in McCarthy's description of Lisp inside Lisp. And now, looking at it this way has some nice properties. Our message sending mechanism is entirely described by sending messages to objects, so we are working within the model we are trying to implement and describe, and by replacing either the bind function up at the top or the lookup method inside virtual tables, we can deeply affect the semantics of finding an implementation of a method for a given message sent to an object. So there's also a reference to a paper on the website which goes into some detail about the neat tricks you can do when you have objects implemented in that manner. But to finish the story for objects, if we were going to flesh them out with the minimum set of methods that we need, messages understood by those objects to turn them into something useful, it turns out that just 4 or 5 messages is all we need. In the same way that we can implement our 5 elementary functions in Lisp, we could write these 5 messages in whatever programming language we choose and end up with a completely working object system. And again, there is a reference on the website and in one of the papers where you can download an example implementation. So the messages that we need, we have already seen lookup on the previous slides. We need to be able to construct a method table. We need to be able to add behavior to an object. So method output should be familiar to anybody who's done Smalltalk programming. In order to create a unique name for a method, it is or for a message rather, it's useful to be able to intern, to create a unique symbol from a string. And then this wouldn't be much use if we couldn't allocate objects. Then all the allocate function does is create some space for a particular size of payload and puts the receiver, which is some virtual table, at offset -1 inside that space. And I encourage you, if the simplicity of this looks appealing, I encourage you to download the code and play with it for yourselves. So what pops out of this is a structure that looks a little bit incestuous. In order to understand behavior inside an object, send messages to it, we have another object, which is its virtual table, which implements our lookup function to give back an implementation for a given message. But being able to send lookup to a virtual table implies that this guy also understands lookup, and so we have a virtual table that describes how virtual tables respond to the lookup. And then this point of circularity in the system occurs here. If we wanted to override lookup, we could easily add, for example, a delegation mechanism that simply says, if we fail to find something in a dictionary, let's go ask some other virtual table. So what do we have so far? We have a theory of functions that dates back to 1962. We have a theory of objects with virtual dispatch, which dates back to maybe 1960. But concretely, we have 2 things. We have some does and some is. We have objects that represent things, they are the is, and we have functions that cause things to happen, the behavior, they are the do. If we look at a typical virtual machine-based language, we might have an image or some class files full of objects, and these represent computations. The virtual machine is a magic wand, we can wave at them, and it causes some activity to happen, some state changes, messages to be exchanged between the contents of the image or these class files. So our representation of does, which itself is an object in many languages, Smalltalk has compiled methods, for example, our representation is indirectly moving things around between the is, the objects, by virtue of having a virtual machine. And the whole system actually would be useless if we didn't have the virtual machine. And the virtual machine itself usually is not described within these systems. There are variants like Squeak, for example, that can create their own virtual machine, and they can run it as a simulation, but really the virtual machine is outside the domain of the objects and the messaging that is happening. And the same is true of Lisp. Inside Lisp, we have a structure that implies how functions might happen, but there is a little bit of magic. The elementary functions and the sequencing of, at the very lowest level, the sequencing of actions that cause those functions to actually churn over and cause something to happen is left unspecified. So maybe what we have here is a situation where the things that are missing in our objects can be described by the functions, and the things that are missing in our functions can be described by the objects. Let's see how that might work. And we could choose either side to start from. Today I'll start from objects. So if we look at an object as a piece of structure that represents something, it is a thing, O, which we can send a message to M, that then gives us back an implementation on the right, I. where the implementation is just a sequence of further messages being sent to further objects. Now, what's missing in this is a story about what the cross means between the O and the M. What does it mean to find the method inside the object? And then what does it mean in the I, the implementation? What does it mean to then cause a sequence of messages to be sent to objects further on? Well, one way we could start to fill this question in is to look at the objects as being the S expressions as described by McCarthy. And then we can say that an object is a structure that describes how to create in the computer's memory some executable form of behavior. And we could even use objects and functions to describe how all of those transformations occur. And then if we feed those back in to the top, we have objects sending messages to other objects via implementations, all described by functions that are created by the structures of objects and the messages exchanged between them. So we now have a circle. We have the parts that the functions failed to describe filled in by the objects, and the parts that the objects failed to describe filled in by the functions. And if we generalize these transformations, we can take S expressions, we can make any kind of intermediate representation that we like, and we can feed that to a code generator, for example, to build something that can be directly executed by the machine at the end. So another analogy that we're quite fond of comes from physical sciences, where we have particles, which are the static description of the universe, and then fields that surround the particles and cause them to have effects on each other. And so the story of objects as form and functions as the behavior given by the form is a little bit like a particle and a field. The particles themselves are uninteresting unless they do something, and the fields really mean nothing unless they can act upon something. So keeping these two things in balance seems to create theories of computing that are very much more powerful than either one in isolation. Now, Niklaus Wirth, if I pronounce that correctly, Niklaus Wirth once wrote a book, by name or by value, depending which side of the Atlantic you're on, that's right. Once wrote on the cover of a book that, let's see if I get this right, data structures plus algorithms equals programs. Well, he was almost correct. He was almost correct. If we take typical elements in the form of objects and dynamic relationships in the form of functions that act on those objects and between those objects, that is the stuff really of complex systems. And if we look at all this as a mathematical unification of the substance of a computing system, many phenomena that were previously seen as special cases suddenly just turn into particular arrangements of these very general ideas. So in a complete computing system, the way this would work, we've seen how objects can describe functions that give behavior to things, including the objects. Well, we can extend that in several directions. We could go leftwards here is towards the programmer. We can use similar mechanisms to provide everything the programmer interacts with, things that parse text into syntactic structures and then operate on those to generate programs. Because there is nothing fixed or esoteric happening, we can use our objects and messages to go orthogonally, and we can describe small sections of our program, for example, where we will deviate slightly. We will describe a new concept to our system, and the system will understand that for a particular scope within our program. So we have domain-specific languages application and what I call mood-specific languages. For the next 3 lines, it is my inclination that this punctuation character means this. I can describe that to my system and it will obey me. In the other direction, we can go find boring languages like C and eat header files directly from our supplied with our operating system in order to interface with the libraries and the facilities supplied for us. So what I'd like to do in the last portion of the talk is to look a little bit how we might tackle going in this direction. And I'll also fill out maybe a little bit of our ideas on code generation. But what's interesting, how are we going to do the lexical syntactic analysis, and then how are we going to do, once we have our structures describing behavior, how are we going to generate something real in the machine off of those. So recently, if you get onto Google or the Wikipedia and you type in parsing expression grammars or packrat parsers, you will find a resurgence of interest in work that was started in 1970 on recursive descent parsing with backtracking, which can understand a much broader range of grammars than many of the tools that are used to construct programming languages these days. Another great influence on what we're doing is the synergy that comes from, that is found in the TeX system by Donald Knuth. Now, TeX is a wonderful way of creating academic papers and entire books, but if you dig a little bit beneath the surface, you will find a fascinating approach to programming system design, because the thing is a functionally complete programming system. And Don Knuth's genius built a system in which the input can actually reason about its own meaning immediately in real time. So the way the input is treated can be affected by the input that has already been seen in a very direct and very first-class manner. So anyone that's interested in how lexical analyzers can be built out of lexical analyzers, go and read the TeX book. It's a very fascinating piece of literature. But what I will talk about in slightly more detail is the grandfather of all dynamic grammar, and this goes to work that was done, I believe, at UCLA in 1962 by Val Shaw, who implemented a system, described a system and implemented it, and built Algol compilers from it, and his system was called Meta 2. And it had a very interesting property that it was grammar that could bootstrap itself. Now, what you're looking at is a little bit arcane. I apologize about the capital letters, but in 1962, programmers actually spoke in capital letters, so this was perfectly natural to them. What we can see, if you've looked at any grammars, formal grammars, you will start to recognize things immediately. We have names along the left, which are fixed points in the grammar. They're called non-terminal symbols. And they can be some pattern that we see on the input. If we see this pattern, we say we have satisfied this particular symbol, and it succeeds in any enclosing rules that we are trying to satisfy. And we feed an entire program to a set of rules like this, and the recognizer says yes or no. If it says yes, we have a legal program. If it says no, we don't. And usually as a side effect, we build some structures that can be used to, for example, generate code off of our program. Now, what Val Shaw did, he built a very simple grammar, and this is it, I copied it as best as I could from the paper, in which what the grammar is capable of doing in its simplest form is specifying a program written in a small stack machine that is capable of recognizing grammars. And he connected the output back to the input, created the simplest grammar capable of recognizing itself. So we see, for example, for our expression 3, we have a set of alternatives. There was no vertical bar in those days, so the slash was used to represent alternatives, which can be either this, or this, or this, or this, or this, or this, otherwise fail. And if we look in the grammar itself, we see here something that looks suspicious. It's saying that we can have one of these, followed by an optional slash, maybe some output. The things in the outs are the instructions that it will generate on the for the stack machine, followed by another one of these. So maybe this rule is saying how we can have multiple different possibilities within one of our grammar rules. And it turns out that's exactly what that rule is saying. This rule here is saying the $ means repetition. It's just a shorthand way of avoiding recursion in the grammar. And it's saying that if we see one of these followed by a $, then we can have as many of these little guys as we like. And here is the rule that recognizes in the grammar one of these things and implements it in terms of these instructions that we see on the right. So what's interesting here is that it's the McCarthy approach to describing how functional programs work, but applied to how grammars work, how computers can be taught to recognize certain sentences and create meaning from them. And we've implemented something very similar to this and used it to bootstrap implementations of JavaScript, Python, and similar languages. Now, in parallel with that work, Larry Tesler and his team were investigating pattern matching in the context of Lisp 70. And one of the systems that they built, the pattern matcher, Lisp 70 pattern matcher, could recognize tokens, sequences of tokens, and from those sequences, arbitrary unstructured sequences create structured expressions, structured S expressions in the dialect of Lisp underneath. So the first half of the slide shows how an algol-like language or a basic-like language could be constructed to translate if statements into Lispy conditional statements. And so if we feed it this, out pops this. Anyone that's done basic will recognize this. Anyone that's done Lisp will recognize this as being equivalent things. Now, this is less interesting than Val Shaw's work for parsing text, and certainly for bootstrapping self-describing grammars, but it's very much more interesting when we think about transformations that are going to take structures that could be in arbitrary form and create canonical structures that can then be compiled to something meaningful for the machine. And this idea came back in 1977, where I think it's Richard Kelsey described a thing he called pre-scheme, which was a kind of scheme that was taken down to the types understood by the machine and used as a substrate for implementing the scheme dialect of Lisp. Anyway, back to Lisp 70. After those initial rules that recognized tokens and created structure, they had further rules. And one of those rules was how to compile those structures into something that anyone who's seen a Burroughs 5000 machine will recognize that this is a little bit like the stack language of the Burroughs 5000. So it's saying that a condition is a series of compilation of the predicates followed by conditional jumps to a label that gets you out of that conditional block. And a less is compile each of its arguments, then fetch the less function, which will leave true or false on your stack. And they used this to build a translator that went all the way down to the venerable PDP-10. Beautiful architecture. Unfortunately, no longer manufactured, so we have to look for something different. Now, what I would say about this is that the stack machine model that they have of output is a little bit limited for what we would want to do these days. It doesn't deal with types, it just assumes everything is a Lisp data type, so we couldn't use it to interface with our machine. It's very simple in its model, but that simplicity, the price we pay, is that everything is stack structured, including control flow. It's hard to generate flows that come out of a block, a lexical block even within the program, and it's difficult to reason with it about data values that might not have neat block structured scope. It's also a little hard to optimize. So, how can we get around these problems? And there was some very nice work done by Fraser and Hansen, who are now at Microsoft, which is appropriate for this room, where they described a retargetable compiler whose intermediate language was a lot more general than the stack languages that we used in Lisp 70. And this isn't exactly the language that they used, but it is very similar to it. And you can see that it's looking much more like the operations that you would expect to see in a stack machine designed for executing C programs. Students of arcane history may remember a project in the 80s called ANDEF, which was a termination of several experiments in creating distribution formats that were independent of architecture, that were completely declarative and had nice mathematical properties, but they looked a little bit similar to this stuff up here. Now, what's interesting about expressing the program this way, rather than as a linear sequence of instructions for a stack machine, is that we can do what we've been doing all along, which is apply some tree reasoning about trees over this structure. One of the things we can do is describe what looks like a grammar, but in fact is picking out pieces of structure within these intermediate representation trees and describing how to generate concrete instructions when we see a particular piece of structure inside the program. Now, whereas the LCC work used what's called a register transfer language, it linearized these instructions and then referred to certain outputs flowing into certain inputs. And this reduced the effectiveness of register allocation, for example, whether you can do register allocation over what's called a basic block, which is something where control doesn't flow into or out of except at the start and the end, or whether you can do global register allocation, which means look at the values within an entire function and allocate the registers efficiently or not, is deeply influenced by whether you use a register transfer language, a linearized sequence of instructions, or whether you use a tree. Now, it's interesting, GCC uses RTL, and I think one of the reasons it's quite slow is because it goes to a lot of work to try to allocate registers in the RTL representation. Anyway, I will say not much more about that other than the system that tries to find coverings of those trees, pieces of structure within the trees, is itself very, very simple. And you can write two functions that do it. Reduce a particular piece of tree to a quantity, a register in the machine, a memory location, a literal in the machine, or a void, just a statement that returns no value. And do that by matching a particular piece of tree against a pattern in the list of rules. These things are recursive, so that structure in the trees can have substructure, etc. And what falls out at the end is a yes or no answer. And it's the inverse of traditional parsing, if you like, where a normal parser takes unstructured free text and creates a structured representation. What this bottom-up system does is it takes a structured representation and tries to find, inside quotes, an optimal unstructured equivalent, which in our case are machine instructions for the target machine. So one of the interesting things that we've now done is we've described code generation as a tree rewriting process, and what we've really been doing throughout the whole talk is describing how various phases of the implementation of a programming system can be described in terms of simple tree-like structures and rules, rewriting rules applied to them. And we can hope in the end to create a single, very small, very easily understandable system, tree rewriting system, in which the whole of the language implementation problem is described. Now, if you choose to go away and play with some of the ideas that I'm talking about today, one thing you will discover is that you need to find a fixed point to get the recursive descriptions started. And the way that we did it was to write a bootstrap compiler in C that could understand a little object language. We then rewrote the object language in the object language, fed it through the bootstrap compiler to create a real compiler, and then deleted the bootstrap compiler because it was now uninteresting. And then everything else, the transformation rules for taking structures, applying all the functional rules to them to create executable things, were then fed in. And from that point on, the whole system takes off exponentially because of the simplicity, the expressiveness that is built into those two mutually supportive models within it. So our implementation, for various reasons, is a little more complex than it really ought to be right now. The language that describes objects and the capabilities of objects and the relationships between them, written in itself, is a little over 2,000 lines of code. The transformational rules that can turn structures, S-expression type structures, into a canonical form for interpretation or code generation, 600 lines. And then a backend that generates machine code. The independent part is a little less than 500 lines, and we have two machine backends that themselves total about 300 lines of code. You add that all up very quickly, that's 1335. We have 3,500 lines of code for a complete system that has the generality that I have been describing and describes in its own model the model that it is implementing. So, big list of things that we have achieved, I think, in 3,500 lines of code. Mark, you can ask questions in a few minutes. I'll leave you to read those. So I'm going to wind up, and then you can ask a question. I'm going to wind up by showing a few slides that, in a tongue-in-cheek way, describe what we're trying to do, at least with the programming language part, the initial steps in our project to rethink the way that we interact with computers. In a typical programming language, I call it the walnut model. Now what happens is that there is really nice, juicy, interesting semantic and implementation stuff inside the kernel, But typically what happens is that there's a shell around it put there by a committee that you will never speak to, you will never get to influence, don't even know who you are. And so there's some interesting stuff on the inside you'd like to get to and exploit, unless there is a hole drilled through the shell for you by some language hacker, you have very little chance. Anyone that's trying to add a feature that was missing to a compiler like GCC will understand the enormity of the task. Now, unfortunately, this little guy with the hammer is just on occasion trying to get something done. He doesn't really care how it's done, except that the only means to do it are hidden away inside. So what are we trying to create instead is a little bit more like a bowl of custard, where everything looks the same, and it's this fluid sameness at whatever level of granularity, to a certain limit you look at the system, it all looks the same, and it can be understood all in terms of the same kinds of particles and the same kinds of fields that describe how the particles interact with each other. And then to create end-user systems on this, you sprinkle a little sugar on tops, syntactic, semantic, pragmatic sugar, apply a blowtorch, and you have a creme brulee. Tastes very nice. Now the difference is, with the previous slide, to make a change in a traditional programming language, you need some very, very powerful tools. Compilers, linkers, assemblers, etc., etc., etc. In the systems that we are trying to create here, all you need is a little spoon. Significantly simpler and found in many more kitchens than a Black & Decker drill. So, to paraphrase, it would seem that less is more. Our experience with these systems are that they are very, very powerful, very, very flexible because of their simplicity and their orthogonality. And in computer science terms, what we've done with many of the features in these systems is to late bind them. What that means is, rather than deciding on policy and mechanism ahead of time, we've thought a little bit about how we can avoid thinking about policy and mechanism, and leave those decisions, maybe provide some default decisions, but leave those decisions in the critical parts of the system wide open so that end users can replace them with their own ideas of what they should be. And in the 4, maybe 5 bodies of work that I've mentioned along the way, you can see that much of that spirit was around in the 1960s and even earlier, and it's kind of a shame that somewhere along the way we lost the vision of those early pioneers. So, some conclusions which are really boring. Objects provide all sorts of goodness which are useful for functions, and functions provide all sorts of goodness which are useful for objects. And combine the two and some magic falls out. What I'd like you to take away from today's presentation is that in a programming system, dynamic really can apply to everything inside your system. Nothing really has to be laid down as law ahead of time. You can leave as much of it as you like open to the people that will use it. And in a dynamic language, the language can also mean all of it, from the characters you type to your system down to the way the system interacts with the surrounding environment. It can be very, very simple, it can be very general, and it will free you from all of the tyrannies of design by committee programming languages that we are forced to use much of the time. But mostly, it's a lot of fun, and if you've never tried to build a language, then take some of the ideas I've talked about today, go back to the original versions of these ideas, download the example implementations that you can find through the URLs on the website, play with it, create with it, and then share it with the rest of us, because there is some innovation just waiting to be happened, and some simplicity that we've lost in computing that is just begging to be found again. So if you decide not to do that, by all means use ours. We'll be trying to make releases fairly often of the system as it evolves gradually towards the platform that we really wish it to be for our main goal, which is the qualitative reinvention of how we interact with computers. And I will leave just a few pertinent quotations up there to entertain the people who are not going to ask me horribly difficult questions. Mark.
So you got this itty bitty number of lines of code. Where is the garbage collection? How are you dealing with garbage collection?
Excellent question. Well, we've swept that under the rug for the moment. Now, I happen to know that your office isn't that far from Hans Boehm. Now, you can ask Hans, how hard is it when you have a C program to garbage collect? Okay, and he will tell you at great length how it's really hard, that's right. So, two things. The first thing is that thanks to Hans and his wonderful work, we have a plug-in collector that we can just, it's conservative, doesn't move anything, generally only throws stuff away that's garbage. In fact, I have yet to see, and this is a testament, we throw some really nasty stuff. Those pointers at offset -1 should break it immediately. I have not seen an error yet due to his garbage collector. So Hans Boehm's garbage collector is fabulous for building prototype systems. Plug it in, forget about your allocation. Okay, it just goes away all by itself. But the second thing is that the lessons that he learned are very valuable. My personal take on this is that garbage collecting C is so hard that even for bootstrapping purposes, use Hans Collector, use the C compiler as a backend to get yourself up and running really fast with your object model, with your little languages. Compiling to C is easier than compiling to assembler. But as soon as you possibly can, throw that C compiler away. Because as soon as you have control over the way your stack frames are laid out, as soon as you know with 100% precision where every pointer is in your program, as soon as you can guarantee that a certain slot in the stack will not, at two different points in time, have either a pointer in it or a primitive type in it, garbage collection becomes an awful lot easier.
So you threw the C compiler away, and you also threw Hans's.
We threw the C version of our, not the C compiler. While we're using the C compiler as a backend, we still use the Hans Boehm collector.
Okay, so the lines of code for Hans's garbage collector
are not factored into that, but they are, yeah, that's right. They're part of the runtime, they're not part of the language system. They're just part of the runtime support, just another library. We could include libc in that as well, we could include the whole kernel in there if you want. But really it's at that level, it's just a library that we use. And sometime in the near future, certainly we will be looking at more closely at the problem of garbage collection. One thing we don't really want, especially for small devices, is a conservative collector. It has to be a precise collector, and for that we really need 100% control over what's happening. So just last week, my displacement activity for not creating these slides was to build a brand new code generator which is capable of generating static and dynamic code. I can just flip a switch and same program, it either runs in real time or it generates a thing I can then execute offline. And that really is freeing us now from the C compiler. Rather than using the C compiler to build this initial base that we can just launch as an executable, we can use the new code generator, and that will have much more precise control over where things are and how they can be garbage collected. Elliot.
Oh yeah, so as one builds on this infrastructure, so one moves into various ecologies for describing different levels of the system. You move from a system which is excellent at describing the base execution of the system, and then when you get much higher, you have a different system to describe its GUI. You have a system of widgets and painters and things, and it's a different universe of discourse. Yeah. So would you claim that a system that is built on this open framework, when you get to those higher levels of the ecology, is intrinsically better? And if you would claim that, what is the relationship between these different levels of scale, and why is it that having the open basis allows one to have a better, higher level?
I could take 2 hours to answer that question. I'm not really sure where to attack it, so I'll just pick some random directions to attack it. Well, no, it doesn't really describe it yet, because so I know for a fact you're familiar with the eToys work that has been done. So one of the things that eToys were constantly battling with was the Smalltalk-like assumptions that were underneath them. eToys wanted to be typical element programming, they wanted to be prototype-based, they wanted to be objects to which you could add and remove methods on the fly as easily as changing the value of a data slot inside an object. But the fact that there were classes behind them complicated things. So if you have a system where the existence of classes really is just where you choose to put a slider in your language space, hopefully will simplify, will eliminate a lot of those problems. Another way of looking at that question is is to think about an end user that comes to a system and sees a particular user interface and wonders about how that user interface works. And wonders about, well, I don't want the close button top right, I want the close button top left. You know, can I move the close button from one side to another? So a very compelling model of computer interaction is that I have a particular funky red key on my keyboard that I can hold down and click the mouse, and what it does, it will peel back a layer in my user interface and show me the relationships of the things that I'm interacting with. And then I click it again and it peels back a layer and shows me the implementations of the interactions, etc., to whatever granularity you want to start drilling down in that system. Now, if we can make those layers as similar as possible to each other, so self-similarity is a word I use a lot, I forgot to use it today, it really reduces the learning curve to understanding how the system at an arbitrary level is implemented. And if the system is implemented in such a way that the models that it's using are designed to be lucid, designed to be clear and easy to understand, again, that shallows the learning curve for anybody trying to get inside it. And if the system really becomes a curriculum, which is one of our goals, then just by reading the descriptions of the interactions between the components inside the system is going to be almost like reading a textbook that describes the ideas and the ideals behind those interactions. But what you're looking at is not just a written model of how it works, it's actually a model that executes. And then any optimizations you might apply to that are kind of irrelevant.
Providing that the level of description at each one of those universes of discourse is equally concise and lucid.
Right, and that, of course,
Depends on lucidity at all levels.
that is a very, very hard problem, but one that by creating a system, you can set yourself up for success. You know, you can create conditions in which your success becomes slightly less unlikely. And one of the ways you can do that, I think, is by creating a programming system in which the assumptions forced upon you by the designer that you have no control over have been minimized. If you late bind as much as you can in the system, then 3 years down the line, you decide, should have been done a different way. There's nothing really there to stop you. And so that reduces some of the impedance that you're trying to shake around between what you envisage in your mind and the way you express it to the machine. So my mood-specific thing, for the next 3 lines, I want to express things in this weird way. Okay, compiler, understand me. I type my 3 lines of weirdness because I have, 1 line of weirdness just before it, or I have a library of weirdnesses that I can call up at will. The compiler for those 3 lines will understand what I mean. And so one of the things, for example, would be a very trivial example would be if inside a program you could say, okay, in this lexical scope inside my program, I want to define a macro, or even better, some active piece of stuff that I can plug into the compiler to recognize forms in the tree that mean and then describe the meaning in terms of intermediate code or even real generated code at the bottom. And then that lasts just like any other declaration. It has a little scope. It says, inside this little bit of stuff here, my weirdo syntax means this thing to the machine. But I could have answered it in 15 other ways, so sorry.
So haven't you built a system for building towers of Babel where, how could 2 programmers ever communicate without learning a brand new language?
Yeah. So that, yes, that is a problem, and it's a subtly, but a very subtly different problem to. Okay, wrong train of thought. But yeah, so it's a very difficult problem, and the slide that alluded to that was the creme brulee, really. And it's true that if you throw too much generality at people, I think Ted wants to say something. If you throw too much generality at people, it can scare them. Okay? If there's no obvious firm footing, firm foundations with some rules, nice tidy rules that you can obey, it can seem daunting and even off-putting to the point that you wouldn't want to use such a system. So pointing that blowtorch at the sugaring really is saying what we're doing here is creating an artificial playing field, an artificial set of rules, and saying in this given environment you play by these rules, these things will happen. But if you don't like the rules, this is how you flip the switch to the dangerous position and start digging around underneath them.
It just seems that when people are given a lot of freedom, they tend to use it, and every individual uses it slightly differently.
Right.
And that makes the interaction and the cross-learning hard. like having to learn a new language every time I pick up a new book.
Right, okay. But then, to draw an analogy, if you look at Leslie Lamport's set of macros for tech, okay, same problem. You could build an infinitely different collection of macros that do essentially the same thing for tech.
Just made it real easy.
Right. And tech makes it really easy for people to break Leslie Lamport's LaTeX system as well. So it's two things. You make the rules that you present people as compelling as you can, so they don't really feel the need to get outside of them, except when that little bit of semantic thing they're trying to get to doesn't quite exist. Then they can go and implement it for themselves, or at least learn how they might implement it. Secondly, I've forgotten my second point now. You make the rules very compelling, and
describe them. You describe them so
yes.
that people can understand them.
Right, exactly. You describe them so people can understand them, but also the rules that people might want to reformulate themselves, being one level down, hopefully would be understandable to anybody else who has looked one level down. Did you have a comment, Ted?
I was just going to say that, yes, the Tower of Babel, but with each language comes its own manual describing what it means.
Right.
As I said,
yeah.
I have to learn a new language every time I pick up a new book. That's the concern.
We'll see.
Not necessarily, because the language, if you like, the particles and fields you're dealing with are always the same.
Well,
It's the relationships, as Elliot said, it's the relationships. that
I've run into this with ontology systems, and what we learned is you have to get the incentives right so that people only extend when they need to extend,
Right.
not just because they prefer to express it in a different way.
Right. Okay, we have 6 minutes left of questions, by the way. I'll go this side and then that side.
We've been down this road a few times in the past,
Uh-huh.
not with great success. I mean, the classic minimal system was Moore's fourth, 9,000
Right.
gates, and we've got a stack machine
Mhm.
and a very minimal implementation, all the way down to a 3-button keyboard with chords. But that represents, I think, the most minimal thing we've seen. And that didn't really go anywhere.
No.
And then we had the whole symbolic Lisp machine debacle.
Fourth was the right
There
in
it
the
was,
language.
you know, layer after layer, and you could go all the way down, and you could get in there in Lisp, and you could get in there in the debugger, and you could hack. And boy, did the AI community burn a lot of useless effort dealing with that monstrosity. And you know, the original Smalltalk on the Alto was kind of like that. I mean, you could go pretty far down before you hit the BCPL level. And you know, we've actually explored this sort of minimal thing that has the same semantics all the way down with no big barriers a couple times. I think Worth went down that road. The thing he did after Modula 3, what was that?
Oberon?
Oberon, yeah. You know, all the way down to the bare iron in Oberon in one system. And all of these none of these have ever gotten any significant market share or utility or anything. Why is this different?
That's an excellent question. I don't know. I mean, if I knew, I would probably be running the next company like Symbolics, if I thought I knew an answer. I don't really know why this should be any different, other than, for us, it's a vehicle, really. We don't see any system out there that currently that is existing that has these features that we need. So really, in many senses, we're building it to have for ourselves as a thing for our further experiments. But we would hope that the flexibility that is built into the system would be compelling for other people to adopt as well, which is why we have done some work on some investigations of running JavaScript inside it, toy implementations of Python as well inside of it. And at some point I'm going to go for a real programming language, real in quotes there, maybe C99, which would be useful for sucking in header files, but maybe not having a narrow-minded vision saying that this is our programming language, this is our system, everything's built in this language all the way down to the metal, but saying here's a system in which you can build any number of programming languages you want with any semantic sets that you want, any group of behaviors that you want inside there, and to make it, to reduce the impedance between what you want and how you eventually achieve that at every possible level. Now, maybe symbolics tried to do that. I never had the privilege of using a symbolics machine, so I don't know. But we don't have one particular goal in mind. Our real goal is to generalize things so that anybody's goal can be accommodated with the least friction possible. I don't know if that answers your question in any way, shape, or form.
This question goes in the direction that was mentioned before. So, how do you see the problem of integration? You know, that people come up with, you know, all these different kind of languages. Like people come up with expressing data structure on a high level, and now you have the problem of like integrating, you know, these two like data structure languages. And do you always go down to your semantic level, or do you have some kind of a notion of, you know, like higher level where they meet somewhere at the highest possible level, or what do you have?
At a very low level, there is the simplest model of objects inside here, and there is the simplest model of functions inside here, and everything builds out from those. So in your scenario, you have two people with differing goals that want to cooperate with each other. The question is they get to choose how far down the rabbit hole they want to dig before they decide to tunnel across and meet each other. But that won't solve the big problems involved in what you're saying. So there is an underlying bunch of building blocks they can use to try and create some object structures, some behavioral structures in common, and if they both build on the same substrate, then intuitively their interaction with each other will be simpler, but that won't solve the big problem. And the big problems are really the semantic payload that comes with the data, what that data actually means. So if I was to take a Java object, give it to a Smalltalk virtual machine, worse, take a Smalltalk object, give it to a Java virtual machine, and ask it to start manipulating that object, then give it back to Smalltalk, okay? I wouldn't trust my virtual machine anymore, because I know that Java implementation can manipulate that object in ways that my virtual machine is not understanding. And it's the same with many pairs of language. If you take Objective-Camel and Lisp, and you try and share objects between the two, there are going to be rules that are sacrosanct in one universe, broken by the other. So there will always be that kind of impedance that you have to overcome.
Maybe there's another set of languages that describe the interaction between the other languages. So we have like a different level of like interaction languages between your languages, and then, you know,
and hopefully it's all part of the same language, because one of the things I didn't mention explicitly, that one of the goals I hope maybe you got from this, is that meta doesn't really exist. The meta level is no longer important, because the level is all there is. There is just the level in which everything happens. Everything you thought of as being meta is just part of your end user universe now.
It's all zeros and ones.
Just zeros and ones, Alan.
Social experiments.
Thank you very, very much for your...
One more.
Okay, one more.
30 seconds.
Anecdotal evidence. I understand that Knut's choice of a programming language for tech was determined by what programming language the best debugger. It really didn't have much to do with what you can express in the programming language, but it's the easiest to debug.
Right, to understand the failures of your program. Okay. So my response to that is that you can take the idea of printf debugging and extend it as deeply as you like into a system. Now what's interesting is that in my system, I can write a tiny little piece of code, and it describes to my compiler, this is how I instrument entry and exit from functions, okay? I point it to a little source file, it runs it. Immediately, I have activation counts for my procedures. I could have edges in a control flow for all my procedures, etc. So really, it's brought, the meta level is down in the level. And if I want to write debugging utilities for myself that are not supplied for me, hopefully now it is possible to do so. So the entire debugger is written in the language, or at least an extension of the language that you are trying to debug.
With that, thank you very much. And
no, thank you. Thank you.
For information on other Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.